right, let's get the ICESat-2 Educator workshop started. We call this a pre-launch Educator workshop because, as you know, in 2 days, less than 2 days now, we're going to launch the ICESat-2 satellite. And that's going to be on what's the big reason why that's so special, other than us folks in NASA who love ICESat-2? About the rocket. Last Delta II rocket, right? So rocket enthusiasts are, it's kind of a bittersweet moment. It's awesome to see that Delta II rocket go up, but then it's also kind of sad that it's the last Delta II. So we're excited about it. So welcome to the workshop, and today it's going to be a combination of a couple things. It's going to be a combination of, I'm going to talk about some ICESat-2 facts and some information about the mission. And then we're going to pass it over to my colleagues, John Moore and Peter Dorofy. They are going to be live from the Palmyra Cove Nature Center in Palmyra Cove, New Jersey. And they're going to be demonstrating something called HoloGLOBE. And then we're going to talk a little bit about one of the measurements that ICESat-2 will be taking, and that's going to be tree height measurements. From 310 miles above the Earth's surface, it will be able to measure the height of trees around the planet. And that's vital for understanding how our planet responds to change. So what's going to happen here is we will start off a little bit about ICESat-2. So as you know, ice keeps the planet cool. Okay? Ice keeps the planet cool in several ways. Ice is cold, right? Okay, but that's not necessarily why it keeps it cool. Okay? It keeps it cool because ice has what's called a high albedo, or a high reflectivity. So the sun's energy, sun's light, hits that ice, and a lot of it gets reflected back to space. When that ice isn't there, what happens? Right, it gets absorbed by the oceans, which then causes the ocean temperatures to rise, but then it also causes land temperatures to rise as well, because we have sea ice on the oceans. Okay, around the Arctic is sea ice. Okay, a lot of people think North Pole is land. It's not. Where the North Pole is, it's sea ice. It's frozen seawater. And then we have two ice sheets on our planet, Greenland and Antarctica. And what that is that's fresh, solid ice on the land surface. Okay, and that melts as well. So there's spots on the planet that are melting pretty quickly, and that's what we're looking at. That's one thing we're looking at with ICESat-2. We want to find out at what rate the ice is melting, or even in some spots gaining. I mean, towards the center of Greenland, the center of Antarctica, okay, we do get some gain because it's really well insulated in those areas. But around the coastlines, we're seeing melting, some places at a foot an hour right now in part of Antarctica, like the Pine Island Glacier. A foot an hour is massive. So ICESat-2, as it moves around the planet, it will hopefully be able to measure these things and help us understand what's happening on Earth in relation to climate change and all that information. So a little bit more about the mission. So as you can see here on this visualization, this is showing you there's reflectivity from the surface. But when we lose that ice and that snow, you can see a lot of that penetrates into the water. That's just a simple little albedo demonstration there. So this is the ICESat-2 satellite. This is what it's going to look like when everything is open, when the solar panels are unfurled. It has 4 solar panels. It has the laser comes out of the satellite. The laser beams, photons, bounce off the Earth's surface and they come back to the satellite. Now, we won't be able to see that from here because it's a low-powered laser and it's going to be 310 miles above the Earth's surface. So we won't be able to see it, okay? But what we have here is that we have to be able to calculate the time it takes the laser pulses to leave the Earth's surface, to leave the satellite, hit the Earth's surface, and back again. So what happens is the satellite flies over what's called a 91-day repeat orbit. So every 91 days, it'll make 1,387 orbits around the planet. And what it does is it has basically these pairs of beams, and it has a reference track. And that reference track always goes between the pair of beams because the reference track allows it to calculate the slope of what it's measuring. Therefore, it can help measure the height of the planet and see how it's changing. When it hits those same spots over and over again, we'll be able to see that change. And very fine change too. Over the sea ice, we'll be able to see changes as small as a couple centimeters. So if the ice melts even a couple centimeters, the satellite will be able to see that, be able to tell, because of that accuracy of the laser beams. So this is showing you what the satellite looks like as it unfurls. It's pretty slow animation, but these are all vital steps for the satellite to actually start working. So your solar panel comes out, then there'll be a door that opens. And the little hole that you see up there is where the laser pulses come out. And then that big dish, the telescope, is what collects the photons that come back to the satellite. So it's firing off, bouncing off the surface, and then coming back to that large telescope in the satellite. So these are all the things it's going to be able to measure. And for those of you who are here in person, we have these posters of this exact same thing, which is really cool. I think there might be a folded poster in your bag. I'm not sure. If there's not, take a couple of the ones here, because we have lots of them, and they're really cool. So, as you can see up here, we're looking at different things, everything from looking at buildings, to ice, to landforms, to clouds, to bodies of water, to the oceans, and to tree canopies. And tree canopies is like one of the most important things that we're able to replicate the measurements on the ground, okay? And we don't have to go far. We, people who are here live, we're just going to walk outside to the courtyard and take some tree measurements. We don't have to go far. And then once the satellite goes over, the satellite will be able to see the trees like that we're going to measure. So we're going to be able to do some ground truthing for that. As you know, we haven't launched yet, so we can't do ground truthing, but we're going to take these tree height measurements. So here's a short video about how ICESat-2 elevates our world. This video was done to show you just how many things it can measure.
From satellite data, we have a very good handle of how our Earth looks like. We can see oceans, we can see the sea ice, we can see our forest. What is much, much harder to measure is how high things are on a global scale, almost impossible.
ICESat-2 adds the third dimension, the elevation. Repeating measurements from ICESat-2 will allow us to measure changes in the ice sheets or in the ocean.
That red one is the reference track that I
ICESat-2
told
is
about. It
designed
always stays
to
there
measure
between
the
the two
changes
lines.
that are going on in the cryosphere, the polar regions.
All the change is at the edges. Those are the steeply sloping parts of the glacier that interact with the ocean, and that's where all the action is. That's where all the mass is being lost.
In order to estimate the mass changes, we need to know the height of things. The mission ICESat-2 carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System.
ATLAS sends out small pulses of laser light 10,000 times a second. And by measuring precisely how long it takes that light to go from the spacecraft down to the Earth and back up to the spacecraft, allows us to figure out what the height of the surface is beneath ICESat-2.
We need to measure the time of flight of a single photon or a single laser pulse with a precision of a billionth of a second.
NASA engineers had to come up with entirely new ways of measuring time very precisely.
A billionth of a second translates to an elevation change precision of just a few centimeters. Climate change is amplified in the polar regions. ICESat-2 is designed to measure those areas and will help us to understand what's going on with our planet.
So that's why we're so excited to get this satellite into space, because we quickly have to figure out what's happening and where these things, this ice is melting the fastest. Where we're losing trees. You know, we lose trees, what do we lose? Oxygen, right? You know, we have photosynthesis going on with these trees all the time. If we lose lots of trees, yeah, oxygen levels go down, okay? But there's other things that it helps with, and I'll show that in a second, looking at tree height. So here's a little graphic I like to show. This is actually one I show for elementary school students, so that's not inferring anything to you guys. But just a clarification, we have the North Pole on the left side of the slide. That's the Arctic. That's sea ice, okay, around the North Pole. And the Greenland ice sheet, which is the freshwater ice. And that's the only place you find polar bears, other than zoos and stuff, but in the wild, polar bears at the North Pole. South Pole is where the penguins live. They don't live together. Coca-Cola did it one time where they had polar bears meeting penguins, and I thought, oh wow, they actually are in the wild together, but then I found out later when I grew up, I was like, nah, no. So it would be predator versus prey there. So in the Antarctic, South Pole, we have the ice sheet, which is Antarctica, and that's surrounded by sea ice. So North Pole is sea ice surrounded by an ice sheet in Greenland. And then in the South Pole, we have Antarctica, which is an ice sheet surrounded by the Antarctic sea ice. So it's kind of opposite of in nature. So here's a cool question for you. As I told you, the ICESat-2 satellite will be firing down laser pulses, right? In each laser pulse, there's photons. And every laser pulse, there's 300 trillion photons, okay, in each laser pulse. They bounce off the Earth's surface and come back. Can we expect to retrieve all 300 trillion photons? Why not? They scatter, absorb, because if they're what? What are photons? They're what? Of light, right? Light goes everywhere, okay? If we were to get all the sunlight that came from the sun directly everywhere we stood, we wouldn't be here, okay? Because it's scattering everywhere. So, question for you is, how many of those 300 trillion photons do you think we're going to get back? Out of every 300 trillion that fire, about on average, how many will we get back to the satellite? And those people on Facebook Live, if you want, just put it on, put it in the comments how many photons are going to come back to the satellite if we fire 300 trillion. 3 million?
1,000.
1,000? All right. He's lowballing it. That's good. I said that's good for a reason.
30?
Oh, you're close. 12. You get about 12. But one thing I have to clarify is that the satellite will fire off about 10,000 laser pulses per second. Okay? That's 10,000 times 300 trillion per second. And if we get from each 10,000 laser pulse, each pulse in the 10,000, we get 12 back. That's a lot of information. So we expect that we're going to get about a terabyte of data per day from the satellite, which is going to be really good for data density. Yeah. So here's a video showing you a little bit about this.
300 trillion. That's about how many photons in each laser pulse fired by the Atlas instrument. It sounds like a lot, but as the photons sail through the atmosphere and bounce off the Earth, they reflect back, just like any light, in all directions. Atlas receives only the photons that reflect straight back to the instrument, just about a dozen photons. That window of photons received must be very small in order to keep the timing error of those photons very small, which allows scientists to calculate elevation very precisely.
So about a dozen. That's a small number, but if you think about it, that's a lot of useful data, coming back every second. So when you get a terabyte of data a day, that's a lot. It's a lot of data. And that's mostly usable data. Okay? We're not sure what percentage of that terabyte we're going to use because we have to see the data first. But with all the tests that we've done, with simulated data, that's what we're thinking we're going to average. So a little history about ICESat and ICESat-2. ICESat-2 is named that for a reason. The ICESat satellite, or I just refer to as ICESat-1, but we only ever call it ICESat, flew from 2003 to 2009 and had a single laser on board fired by the GLASS instrument, the Geoscience Laser Altimeter System. And that single laser took measurements every 170 meters on the ground. Okay? So basically at each end of a football field, okay, it took a measurement about that distance. And that only fired 40 laser pulses per second, which compared to the new one is, not much at all. But in 2001 and 2002 when they were building it, that was the technology that we had. Okay, we didn't have the technology to do 10,000 laser pulses per second. We had 40, okay, and that was really groundbreaking then. ICESat-2 has, and the last video mentioned it, the advanced topographic LiDAR altimeter system. I think it's laser altimeter system, not LiDAR, but Atlas. And basically what it is a single laser that's split into 6 beams, which are arranged in pairs. And they will take measurements every 70 centimeters. So it will overlap like at every yard line on a football field. And this will show you. So we have in the middle, if you look at the middle here, this red circle is where, this red circle, then this red circle is where ICESat-1 took measurements. That was how far or hard it took to go to how it fired a laser. Here is showing you ICESat-2. So there's going to be a lot more data coverage and a lot more data, elevation data, height data, that's been coming back from the satellite. So, we always like to have fun, and we're not all serious all the time, okay? Even though we're a science agency, we like to have fun, but we like to bring audiences in that we don't really see often, okay? And as really younger kids, we try to create videos, visualizations that tie into something that's fun, that they can follow throughout the life of the mission. So we created a character called Fo the Photon. Okay, we actually have a page for Penguin too, that's our mascot. Fo the Photon is kind of our spokesperson. And this shows you what a photon has to go through, okay? Now, before I show this, please don't think of, don't even think of the scientific liberties we took with this video, okay? And you'll see what I mean in a second. But this is a cartoon, an animation that's called Fo the Photon, it's called Photon Jump. This is a cool way just to show what a photon has to do.
Attention photons. Prepare to measure Earth's changing ice. Laser pulse 22A4 departs in 5, 4, 3,
Have a seat wherever you like.
2, 1.
So photons probably don't scream as they're flying through the air. But remember, all this is happening at the speed of light, so who knows, right? Usually kids open their eyes really wide, like, really, that's what happens? And then I have to dispel that myth. You gonna make it? Apparently, photons have arms as well. Yeah. This is a great video to show the kids. They love this video, but they get interested about the mission.
Excellent job, Fo. Your travel time has been recorded. Let's add it to the elevation data set. Ready the next group?
So this video was created through a summer program that was kind of like an internship, a program collaboration we did with the Savannah College of Art and Design, SCAD, out of Georgia. So yeah, we worked together with them, and we storyboarded this and all this, and made this cool little video about it. So it's pretty fun to see. All right, so now what I'm going to do, I should mention, ICESat-2, we're launching Saturday, that's the launch. Once you get into space, you're going to, if everything works properly, which it will, okay, we're going to get a ton of data in a short amount of time that's really going to help us understand how our planet's changing. And at NASA, we have Earth-observing satellites that have come from all over and looking at all different parts of the planet, from the oceans to the clouds, to the carbon budget, to ocean color and phytoplankton, looking at algal blooms. Right now, there's lots of satellites out there looking at the hurricane, Hurricane Florence that's about to hit the coast, in the East Coast. I'm from the East Coast. I'm from Maryland, live in Maryland, work in Virginia. And Jeremy is as well. So we all live over down the East Coast. So we have and I live 30 minutes from the ocean. So in Maryland, so it shouldn't be, let's get a lot of rain there. But we have satellites looking at things all over the planet. And every one of those is a piece of the puzzle to help us understand what's happening on our planet, how our planet is responding to change. So you'll see when we go over, if you stay for the open house afterwards, that's next door, there's lots of stuff about ICESat-2 that, lots of branch out projects that we can do. Like we have hands-on stuff that you can do with students, you can do it with adults, anything, anybody. So hope you stay and check that out. But now what I'm going to do is, I'm going to pass it over to my colleagues, John and Peter. And John and Peter are at the Palmyra Cove Nature Center. And they're going to talk to you about something called HoloGLOBE and MergeCube and the ICESat-2 mission. They're going to show you it's a virtual reality thing that is super cool. And we're going to switch over to them. I have to pop over here to my laptop, switch over to them, and we will go there in a second.
Hello?
Hi, John. You guys good?
We're good.
Yep, you're on screen right now.
You're good. Yeah, we always got a 20-second delay between Facebook Live and Zoom. Zoom seems to be sick.
Okay.
We're on the same page now. So hello from New Jersey, everybody. We're happy to be with you tonight. Taking you through a couple of things. I want to share our screen with you. Show you a couple of slides and tell you about how we're involved with Brian and kind of sets him up for a little bit later. And so we'll get started. One second. You see it? Are you seeing our PowerPoint?
Yes.
See here. It's, I'm not sure that this set up.
Yeah, I think we're good now. Looks like we're-
Yeah. Can you guys hear it all?
Still hear us, correct?
Yes.
Yep. Yep.
Okay, let's come. Go ahead.
You're good. Go ahead.
Okay, so we'll get started here. So first of all, our connection tonight is with a NASA program that we work with called Mission Earth. You can see the title of it. That's a NASA CAN grant. And this is focused on education. And as you see, it's looking at the GLOBE program, which Brian is going to talk to you about and show you the tree heights. But with NASA assets, as it says, I'm not going to read the slide to you. The GLOBE is a NASA acronym for Global Learning and Observations to Benefit the Environment. And the history, it has a long history of scientific protocols that use students and teachers out in the field making observations and enter data that global change scientists and other scientists use. So one of the important parts of this work is, there are other projects in GLOBE that you have opportunity as students, teachers, or citizen scientists to basically validate through doing ground observation with satellite data. From the teacher's satellites, one of the lines I usually use is what the satellites tell you. They don't tell you anything. They need somebody on the ground to interpret that data or verify what's going on Earth. So this is an educational model that we use, space to Earth, Earth to space, meaning that we can look from satellites down to Earth and get global data sets, but then from Earth we can validate those data points with what these are the satellite data that you can track. More than ICESat, but the purpose of tonight is to introduce HoloGLOBE, but also this week for you in California there for the launch, to introduce the ICESat-2 component to this. Now, of course, the data won't be coming in for a bit until they get established out there, but when they do, you'll be able to see it on this tool. One other thing to talk about something that's coming next. In fact, it was released just today. It's almost breaking news, and you see another Facebook Live opportunity for next week, September 17th. But this is a Globe Observer app that looks at land cover. And Brian's going to teach you about the tree height. We already talked about that. But of course, I think it's easy for you to see and understand that using the land cover app will give us another layer of robust data that we can look and put these pieces together. And the idea there is, as Globe says, to observe the Earth and make measurements, and then have everybody involved with that. So I'm going to turn it over to Pete, and he's going to talk to you about HoloGLOBE and give you a little demo of how it works. So here's Pete.
All right, thanks, John. Okay, so let me just exit out of here. And the first thing I would like to just go to is the Merge website, where the Merge Cube actually comes from. As John was showing you, basically a picture of what the cube is. But anyway, the cube is, if you are familiar with mixed reality or augmented reality, for example, is my video coming through? Is everybody seeing the? Okay. It's the most familiar augmented reality app that many people are familiar with, and kids certainly is Pokemon Go. You're walking around with an Android or iPhone applications, the Pokemon character pops up on the ground, and do some activities with it. So that's augmented reality. So this cube is being used to render images or models such as that onto something that you can actually hold on to. So the cube is your tactile base, and then you can render all kinds of content on top of that. So there's all types of apps that you can get for the cube. Most of the, many of the apps that you can get on the cube are really a lot of cool, fun and games, activities that you can get for the cube. But there's very few in the way of educational activities that are out there, and so we want to use something that we were interested in the cube because the tactile feedback, and to get some educational content onto the cube that doesn't really exist right now. So anyway, if you have a chat, definitely go to the cube, the Merge Cube website, and someplace here, the HoloGLOBE is on their website. Let's take a look. Here, that's been too much time on this. There we go. Okay, so here's HoloGLOBE right there. So you can click on that and do a little bit more about it. It's available on both Google Play, the Google Play Store, as well as the iTunes Store. Either of those will have it on there. So after you go, you actually go. So right now it's linked to the Google Play Store, but you can actually visit the website, read more about it, see some of the sample imageries that come from it. So for example, this person here is holding onto the cube. She's seeing the visible Earth. So instead of me blabbing about it on the website, let's go right to the actual app. And to do that, I'm going to pull up my app editor just to get it playing on here, since HoloGLOBE was written for Android and iPhone and not written for the Windows PC. I have to actually use my editor to demonstrate this. So show you this. Okay, well, it's at 20 second delay. Okay, so this is what you're going to see. This is the first thing you're going to get here is a nighttime view of Earth. Now, HoloGLOBE is actually getting all the data sets from the NOAA's Science of the Sphere program. So that's what's really running on these SOS programs. So this is an example of one that is this blue marble at night. So I can, on your phone, you can touch screen, you can actually drag it around. I'm using my mouse to drag it. I can click on the info button. So again, you can be touching it with your finger, for example. Again, just turn the touch screen. Read a little bit about what info box here. So this top here, this is like your main menu. And you'll notice that around here, these little boxes, these are what I like to call modules. So in particular, there are two types of modules that are set up here. The first set are data sets. So these are all real or near real-time data sets. So for example, if I click on the clouds button, I can get real-time clouds, again, directly from NOAA's website. I just take a moment. And so again, we can read a little bit about it, but this is from the SUBI NPP mission, which is the global cloud coverage for the past 24 hours. And if I just move it around, you can obviously see some of these hurricanes, like Hurricane Florence right now, all the tropical storm. So again, it's near real time, which would be cool for kids to look at in real time data. I can then, if I want to click on some other things, I can click on these arrows here to advance through activities that are built into the modules. So these are the modules that surround the Earth, and then these arrows will click through different activities. The next activity is a cloud model, forecast cloud model, which will actually animate once it downloads everything. So a couple other features is that we have these two overlay buttons, so I can click on continents or country names. I can click on air currents, ocean currents. So all types of layers that you can interact with and compare overlays to actual data sets. So if I want to, for example, use air currents to track the ocean of global cloud coverage, I can do that, which is cool. Okay, so now I'm going to say that there are various apps that are already out there. You can do a search on NOAA, NASA, Earth, satellite data set, and you will get, you can download things like this already. But what makes HoloGLOBE very unique is that this is linked to Merge Cube. So what I'm going to next do is demonstrate to you by taking the Merge Cube and placing it in front of the device camera. Do this right now. You know what? I just realized I have to stop the video. So here's what's happening. The camera is being shared by both the editor as well as the Zoom app. So I have to stop video on the Zoom app. You should still be able to hear me though. I just stopped the video, so I'm now giving the camera, the editor, the app to take over. So hopefully that'll now kick in just a moment. So let me just restart this. Clouds, and let's go ahead and place the cube in front of the device camera. Again, it's because I had to switch out of Zoom to the, there we go. So now, it's a little slow, only because, again, the camera resources are being divided, but, so we actually hold on, by holding on to the cube, we can actually hold on to this real live Earth. We can use tracking and move back to normal. Here we go. So that's kind of cool. And I can go ahead and move the Earth to this days button up here and bring up all my modules back. Now this is a little choppy again. If you use like Android or iPhone, it'll be a whole lot smoother. This is definitely try it out. So I'm going to go back to normal mode here. And then there are very solid modules here. There's another quick one is GPM. I click on GPM. There's actually videos. You can actually add students watching video of the GPM mission, for example. Again, they can hold on to the cube and see this running. And finally, this is a tunnel other numbers on the app. So I'm going to click on the ICESat-2 module, which is one Brian wait to see. So here's ICESat-2, we'll click on that one, and there's a whole set of activities that you can then go through about the ICESat-2 mission. So you click on the icon, the info button there, you can do a little bit about it. And what's also included on the HoloGLOBE is ICESat-2's mascot, Poe, the photon. So you click on next, and here he goes. So Poe is now zipping around the globe, and you can click on the info button and learn about Poe. And you can, if you want, you can take the tune back and put Poe in augmented mode. Oh, let's bring it back. There we go. You can just page over there and read more about the ICESat-2 mission. Over that. So anyway, it's fun just to kind of click around there. And it takes time to, get to know the functionality of HoloGLOBE. HoloGLOBE has a lot of features to it, a lot of cool things to do on it. And it's just a matter of playing around with it. You can also see some simulated data sets. We can click on the next arrow and see some simulated data. That'll come up in just a moment. Here we go. This is a cross-sectional scan of elevation. We can read about that right here and click on the button. Back out of that. Anyway, so that's what we have. So again, just have fun and clicking around things, learning about cold orbiting satellites and geostationary satellites and all kinds of activities to try out. So I'm going to, John, you want to jump in on that?
And just wrap things up, one thing Pete didn't mention is that this is a free app, and again, it's available on Google Play or Apple iTunes Store or the App Store. And the point here, just to wrap things up, is that what we're trying to do as educators is get this type of real, authentic science into the hands of students and teachers and citizen scientists that they can participate in authentic science. So a little later, Brian's going to be taking you out so that you can participate yourself in hands-on science. But rather than sitting in the classrooms and reading books, we can use these amazing NASA resources and data sets and get students to be directly involved with the real science. So with that, we'll end here from New Jersey, and Brian will send it back to you.
Yep. Thanks, John and Peter. Does anybody have any questions for them? Anything about HoloGLOBE or MergeCube? So I'll have the website that you can go on to it to show where Peter and John were showing everything from, so that you can grab all the information from that. Anybody have any questions about that?
Why don't you pass out a sheet with the website?
Well, we'll have it up here. NASA has a Paperwork Reduction Act. That's my answer. We don't want to print a ton of things, so the website will be up there. If you want to copy it down, that'll be fine. All right, any other questions? Great. Thank you, guys. I'm going to go back to the presentation. All right, thank you. I'll keep the Zoom open. All right, so yeah, that's a nice hands-on, literally hands-on way that you can look at NASA data, and the ICESat-2 one is the newest part of HoloGLOBE because we want to get it set up so once the real public release data comes out, then it can be ported onto that program, and then students can hold the globe in their hand and see what all the ICESat-2 data is. We're going to get that terabyte of data back, but so this will help us to basically take the science that we do and make it a little more understandable for kids in school, because NASA has a lot of data all the time. Okay, so ICESat-2 data on there will be super cool once it comes out. But the website will be up here in a second. But before we do that, John mentioned the GLOBE mission, and that's why it says, HoloGLOBE. And if you don't, anybody know what the GLOBE program is? Okay, great. GLOBE program is Global Learning and Observation to Benefit the Environment, and it's an international program where students, educators, citizen scientists take measurements out in the real world of environmental conditions, of up to 50 different measurement protocols, and all that information is then sent to the GLOBE program at NASA, where anybody can access the data that you submitted from your environment. So students use it for research projects. Let's say they're researching, let's say a school in Michigan, like Shoemake Middle School in Michigan, where my friend Mr. Jeff Bauman teaches. Say they're doing they want to understand what's happening with water quality, compare the measurements they've taken with water quality with measurements in a school from Nigeria or South Africa or Croatia. They can go grab that data right off the website and then do some comparisons. So it's great for research projects as well. And students do it all the time. The GLOBE program has something called the International Virtual Student Symposium, where students submit basically science fair projects, but virtually. And then a whole judging process. Professionals like myself are judges, of these projects, and they get judged with students from all over the world. I can't remember how many countries the projects came from, but GLOBE is in over 120 countries right now. There's over 120 countries with students taking measurements. So here's a quick video to show you what GLOBE is. And this is basically from the aspects of teachers and how they've been doing it.
The GLOBE program connects students, teachers, and scientists from around the world through hands-on science research activities called protocols.
We're sampling invertebrates, and then we're looking at our key and deciding what they are, and then we're going to put it on the GLOBE website.
And so they're looking at data that students around the world have collected, and they're seeing how their data is going into that same pool. And so now they're part of this global group of students who are monitoring all parts of the ecosystem.
No matter where we live, our common bond is the Earth, and GLOBE allows all of us to discover and learn about the air we breathe, the water we drink, and the soil we use. GLOBE connects us to our planet and one another through interactive exploration.
I think it's cool to see that everybody all around the world are doing this just to help the Earth.
The GLOBE program encourages students to be curious about the things they see every day, like clouds, streams, and plants. Through the data students collect, GLOBE helps build a bridge between today's science research and the next generation of scientists, because professional scientists are able to access the data collected by students around the world. In turn, students become more engaged and involved with science.
To know that, a NASA expert or a GLOBE expert is going to use that actual data, that's really exciting for the kids and us.
Take the first step to encourage your students to discover, explore, and investigate their world. Do GLOBE today. Don't just read about science, do science.
So I show this because when the ICESat-2 data comes out, and then we have students who are going to go out taking, and citizen scientists eventually taking tree height measurements, the NASA scientists with the ICESat-2 mission and other scientists as well are going to be able to grab that data, because that data will be basically geolocated when you take the measurements. So the scientists will know what the latitude and longitude is of where the tree is you're taking the measurement. And then they'll be able to compare that to the ICESat-2 satellite data. So that's why it's super important, because that one helps to create a second level of data validation for the satellite, but then it also allows students, educators, and citizen scientists to feel as they are part of a NASA mission, and they are, okay? If they're taking measurements and NASA's looking at their data and looking at that information they're submitting, they're part of the mission. okay? We want as many people as possible taking tree heights. We actually have a bunch of people taking tree heights already for the GLOBE program and part of our ICESat-2 program, which we're just starting up. It actually, the measurement, I'm not going to show that one there. It's okay, there. So, okay. So we have a project called Trees Around the Globe, capital GLOBE, okay? And that actually starts when the satellite launches. So that is basically where students are going to be taking tree height measurements as long as other measurements in their environment, because we like all that extra data. Not just tree height, but then we offer protocols in GLOBE, one's called green up and green down. Okay, so it's a seasonal thing. You're looking at the trees seasonally, when the trees are, the leaves are coming out, blooming, the buds are coming out, and then also when they're falling off, so green up and green down. But also, we like to figure out where the trees are, what's happening in their local environment as far as like air temperature, relative humidity, soil temperature, surface temperature, things like that. These are all GLOBE measurements that students are taking all the time. And when you combine those with the tree height measurements, that's our campaign. So we're going to have people from all over the world looking at this. So tree heights. This right there is showing you, there's a laser here. No. But this right there on the left is showing you, ICESat-2 flies over and it does this, the footprint, which is 17 meters. So that means it's 17 meters on the ground. Okay? That's what that footprint is right there. You see in that circle, the brown circle. And then, so it'll take the measurements of the height measurements of those trees. The photons will bounce off those trees and up again. Okay? We might not hit every branch. Okay, we're going to try to get the top part of it. That's why we have repeating tracks. It goes over and over again. Okay? So looking at tree heights is not just for the sake of looking at how tall trees are. That helps with a lot of things. The growth rate of trees in a particular area, looking at Amazon rainforest versus, here in Lompoc, okay? The environment, the biomes are completely different, okay? But then we can also look at stand exams, which are used to characterize forest vegetation for use in wildlife habitat. The timber industry uses it as well. Structure of forest helps us understand our carbon budget. Because where there's trees, where a lot of the leaves fall, that creates a blanket of carbon, basically called humus. Okay, so it creates that high carbon. So we're trying to find out our annual carbon intake and outtake all the time, and trees help us do that. Tree height, because we know how tall the trees are, how it's growing. So that's why we decided to do this campaign, because it's such an important variable. This clicker's a little slow. There we go. So this is a lot of text from here, so I'm not going to go through everything, but ICESat-2 will measure tree height. The GLOBE program has a protocol called biometry, that at one part of it is a tree height measurement. And you can do it many different ways. But when you combine GPS, basically where the tree is, with the tree height, that's the data that we need, okay? Because that data they can be compared to this NASA ICESat-2 satellite data. And as I mentioned, they can use it to design a project. So here's just a screenshot of our campaign page and how to get involved with it. And that's the website down there. I have it at the end of one of the slides too, but that's our website. Forward www.globe.gov/web/trees. I didn't come up with that URL, okay? That was one that came from the GLOBE program, just the next one in the cycle. So this shows you here, all the things that we're doing. We'll be able to look at the protocols. We're going to have webinars. Actually, our first live webinar is going to be Tuesday, the 25th of September. And I don't remember the exact time. It's on the webinar page, so. But then we're going to have it set up that you can go and look at other GLOBE tree height data that other students and citizen scientists and educators have submitted. Then you can eventually look at the NASA data once the satellite data comes out. So then students can do some comparison just by going to this kind of one-stop shop for this campaign. So this is the tree height measurement, which we're going to go outside and do. But what it is we go outside, and when students go outside, they take measurements to up to 5 trees in a particular area. And then they go back and measure those trees over time, like, you know, every couple of weeks throughout the school year, maybe the next school year, then the next school year, or in their backyard, things like that. So we focus on 5 trees, and you know, we have certain parameters here, a distance of 3 meters between each tree because of the 17-meter spatial footprint, so we'll be able to, you know, the satellite will be able to differentiate the trees as well. So it helps with that spatial resolution. So here's just showing you, you know, type of tree canopies that we can measure. So this is what we're actually going to use to go outside to measure. It's a clinometer. Okay, this is just a paper version of it. This is the one that we have on the GLOBE website. It's anything you can build. So we have them up here. I have took a picture of what it looks like just built. So all this is clinometer with a straw tape to the top. That's going to be your line of sight. Then we have a string with washers on it. And that just hangs down at the 0 section. It's kind of slid over there for these purposes. But I have it over at 45 degrees because when we're measuring trees on a level surface, when we hold the clinometer up, we want the clinometer to read 45 degrees while you're sighting the top of the tree through the straw. And then I'll show you outside how exactly we can figure the height of the tree just by doing that. So it's really simple. It's just simple trigonometry, but the easiest way to do it is because out here it's going to be flat, so we're going to do it what's called simplified clinometer technique, so it's on level ground. So you're each going to get one of those. I have some built, so you can take one of those with. It's very simple to use, and then we'll go outside and do that thing. So these are the different ways you can measure it because you know all ground isn't level. Simplified clinometers, what we're going to use is simply a level surface, and then we have one called standby tree. Then we have a 2 triangle with eyes lower, so basically you're standing here and the tree's up here. And then there's another one, you're standing up here and the tree's down there, so you're above the tree. So that gets into a little more you know, complex trigonometry for measuring trees, but we're going to focus on the simplified clinometer one right now. So we're going to go outside in a couple seconds and measure some trees. This is just an example showing you what the data sheets look like on GLOBE. They're pretty precise, okay? But these are what you're going to see if you're on GLOBE. And then it's just an example showing you what the data sheets look like on GLOBE. They're pretty precise. Okay. And this is showing you that we have lots of things going at one time. It's bound to happen. And this is showing you what the data entry is. Just asks for the height of the trees. Why do you think it asks for each tree? It asks for 3 heights.
Average.
Yeah, accuracy, you just want to like average that because since you're doing it with a paper with a straw, a string and a washer, okay, it's not the most advanced scientific instrument, but it's cool because the kids like to use it because they get to build it themselves. It's pretty easy to do too, and it's a couple cents to do it. So then we're going to go outside and measure some trees. But first, as you know, sorry, I don't know, it's 40 minutes, it's like a 2.5 hour minute, 2.5 hour launch window. ICESat-2 satellite launches, as you know, at 5:46. The launch window opens at 5:46 on Saturday. So actually, do you know, Jeremy, it's like a 2 hour and like 30-minute window? It's something like that, I think. I think it's pretty long. I think at one time it was 40. I think it just got changed. But I'll leave this one up here, if I can get to it. Yeah, I'll leave that up there. That's on the website, so it's kind of long. But I'll leave it up, you can come in. But what we're going to do now is we're going to go outside. That's good. We're going to go outside. If each one of you want to come up here, I'm going to hand you a clinometer. We're just going to walk right out these doors into the courtyard. This is going to be yours to keep. You know, it's not a big gift, but it's pretty cool. I'll hand you that one.
The launch window is 5:46 to 8:20 a.m.
So 5:46 to 8:20.
Yeah.
Okay. So like almost 3 hours.
Little less, yeah.
A little less. Yeah. All right. You can leave your stuff there so we can come back in, or you can leave from there. But either way, I'm just going to show you how to do these little measures. So this, when you come in, you can grab some of these posters and We're going to go outside and take some measurements using this clinometer. This is what the kids like to use. It's pretty simple. Anybody get one yet? Yeah, I'm going to take the tape measures out. Yep. There you go. All right, so let's head outside. Hopefully for those of you on Facebook Live, you'll be able to follow us. The camera is coming this direction, so the Wi-Fi should come out here. I'm going to keep the headphones on. All right. So I'm going to show you how well it takes a little learning curve to learn how to use these, like put your eyes up to it, right? But let's start with this tree right here, because this is a good transition tree because it's in the sun. Those over there in the shade are a little smaller. So what you're going to basically do is you're going to go to the base of the tree. Okay? You're going to go base of the tree. It's a little windy out here, so you should maybe work in pairs. You don't have to, but you can work in pairs. But your object is you're going to walk to the base of the tree, and you're going to line up. Okay? You're going to line up like the tallest leaf that you can see through the straw. Okay? It takes a little bit of practice to do. And it's a little windy out here, so it might wiggle around. But what you're going to do is you're going to start off by looking through the tree, up to the tree, and you're going to back up or move forward while keeping the top of the tree in focus until the string hits 45 degrees. That's why it's good to work in pairs. One person to do it, and the other person to watch the string. And make sure your string's under the straw, like just at the edge of the straw. Sometimes it might have flipped up. So it's a little tricky to do since it's a little windy. Anybody want to try it? And then what we're going to do, let me tell you how easy this is. Once it's around 45 degrees, okay, you stop. Then somebody else takes a tape measure and they run it from the bottom of the tree to your feet. Okay, they take that measurement and then they measure from the ground to your eyeballs. They add that measurement to that measurement, and that's the estimated height of the tree. Pretty simple, right? Just trigonometry, you're just measuring angles. That's all you're doing, okay? But that only works how? Yeah, on a level surface, right? This isn't the perfect level because we see we have a little dip there. It's down in the soil a little bit, off the cement. So, does anybody want to try? You all can try this, and you don't have to do it from the same spot. You can walk over there and do it, walk over here. If you wanted, you can do one of these little trees here too. Okay? But if you want to work together, it might be easier so you can see. If you hold it like this, you're going to hold it like that, and you're going to look through that straw. Yeah, that's the hard part. Yeah, the string should always be over to the right. And you look up, you walk up to the base, like up to the base of the tree, you put the kilometer up. You find that the top of the tree, the leaf, it's hard because it's windy, and then you back up, and when it says, what's your, yeah, is it tricky?
Well, as soon as you try it, we can lose it.
Yeah. I'm going to show you a tool in a second that you can actually buy online for about $4. It's a clinometer as well. It's not the paper. The paper's kind of tricky when it's windy. Yeah. It's also too that, well, you guys are pretty close to the same height too, so that should be pretty close. You're at about 40. There you are, you're about 42. There you go, 45. Okay, so yeah, you got it.
Checking to see if we got it right.
Yeah, so then you use a tape measure. So, you know, a tape measure. Yeah, let's see what his measurement is, then we'll compare all of these and see how it works. Guys and troopers were doing it in the wind like this. If your teachers don't take them out during a thunderstorm to do this, that would be very hard to do. You guys get anything close to each other? Yeah. You're at about, yeah, you gotta go this way. Yeah, towards him. So you're at about, stop for a second, you're at about 30. So you gotta walk a little bit, you gotta walk further, closer this way. Towards the tree, yeah. That's pretty close. Yeah. You got 11 feet. Okay, and then you gotta measure it from the ground to his eyes. And then you add those two together. And that'll be the height of the tree. Your measurement yet? Okay. 12, okay. Is that distance that way? Do you add that? Okay.
I think that's not going to be average.
About 5.5. Make that sound right. Get close to your eye. Yeah. About 5. Yeah, about 5. There you go. About 5, 4. So your distance was about 12. Let's say 12 and 5, so like 17. Oh, you just okay. Just hold that there. Here. Okay. Not half 5, so 5, what, like 15, maybe 15 years is 12, 5, so like close to 17. So like, Yeah, true, and plus it's torn like this, and yeah. But that's pretty close because you all are within like a foot. So yeah, that's pretty good. Yeah. How do you guys do?
158, 162.
Okay, that's pretty good. They were all within a foot, so. So when it's not windy, let me show you this guy here. This is a cool clinometer, but this is something that really takes some explanation. So it's a handheld plastic one, and it has a sight that should be like this straw, okay? But it's always looking at 45 degrees. Then you have a level here. Okay, there's a level, and then there's a mirror right here. So your objective is to line up the top of the tree and get the bubble in the middle of the level while looking through the mirror. It's fun to do, actually. So, yeah, so if you go up, you just look up through this, and I'm looking at the top from there. The bubble's not there yet. Oh. Out like here. So, yeah, you guys want to try that one out? Yeah. We have a couple of these here.
So we're getting this data, and we're creating it into the
Globe.
just the regular Globe website?
Yeah.
Okay, and the coordinates and stuff will,
Yeah, the coordinates, it'll ask for that. And what you can do for that is, there's apps on your phone that you can do that. And, I have one, it's just called coordinates. And then what you do is, you just walk to, the base of the tree, just hold it there, then move it to the middle of the circle, and then it tells you exactly what the latitude on it.
okay, and then that's when you would enter into the Globe.
Yeah, you go on this there for latitude, and put that number in the longitude, put that number. That's all you do.
Okay.
So then it becomes basically geolocated.
I see. Okay.
Yep. So you can see here this map. You can wait where I'm standing right here. It says back and just bring that up. It's just called coordinates. It's a free app. Google or where? Yeah, it's free app. You just go to whatever your phone is.
Oh, I just read it.
Go to where you get apps. It's like Google Play or Android or just go to Google Play and type in coordinates. And the first one that pops up.
Okay.
Yeah. It's pretty cool because all you do is it shows where you are, and then you put it right in the middle, and then it shows you exactly how you want it to do. So yeah, it saves a lot of holding a yellow GPS there for 25 minutes. Figure it out. So.
Yeah, it's always supposed to be.
Yeah. Oh, funny. Interesting. Cool.
Yeah, those are like, you can get those online from like, I think Forestry Supplies for like $4.
Cool.
My school, when you do it, just.
Oh, yeah, sweet. Yeah,
Because I don't have $4.
yeah. Well, yeah, the kids love that. I mean, they love to build it. And then, yeah. All right.
Yeah, but even, we never
No.
like every 4
Yeah. Yeah. All right, does anybody have any questions out here while we're, yes?
The little cube
Yeah.
in the hallway,
Yeah.
you said that that's what we can get online?
Yeah, it'll show you, you can actually get those merge cubes, like the foam cubes, like at Walmart
Oh,
and things like that. It's just called a merge cube. Yeah, but if you go on that website, the URL that's up there, it'll show you, tell you all about it and like where you might be able to get it. But I'm pretty sure, and they're cheap.
If you shop online on
Yeah.
Amazon.com,
Yeah.
it's about $10. But you can get 2 of them for $18.
Yeah. So, and I should tell you though, they actually, I think on that website, they have paper ones that you can print and then cut out and then tape them as a cube. And then that's what we're doing. We have an event in Solvang tomorrow night. It's the Beautiful Earth program. And we've cut and pasted what I have, and my colleagues did 500 of those today. Yeah, they made 500 cubes, so everybody in the audience is going to get a cube, and they're going to do something in Halloween. So, yeah. That's not even mine. I wish it was, but it's a. All right, any last minute questions? Are you guys gonna check out the open house next door? Yeah, that's cool. It should be underway. I think it started at 5 o'clock. But yeah, yeah, I go around that way. But hey, is there one more? Oh, that's your tape measure. Okay. Up here, there's a couple of posters and some stuff. Take anything you like, not my water bottle, or the clinometer. You can take an extra plastic clinometer if you want. Yeah, but there's some other stuff. Your posters, electromagnetic spectrum booklet, some cool observations, some NASA stickers. There's one in there, but feel free to take more. And you just want to take one of these bags. And we're going to sign off on Facebook Live. Thank you. Thank you for joining. And ICESat-2 mission launches 5:46 a.m. Pacific time, 8:46 Eastern time. And, you know, crossing our fingers, hope for the best for ICESat-2, and take care, everybody.